Mr. Gibson here. Today we're going to look at part 2 of this unit on linear motion and specifically understand what motion with acceleration looks like. So let's look at our objectives. First is define acceleration and give examples of its units. The second is to solve some problems that deal with acceleration, velocity, and displacement. All right. We are going to start with a simple model, right, of a moving man. And let's say as he runs from left to right, we take a snapshot of where his location is or displacement is every second. So if we got this type of picture, what will we conclude about his motion? Well, if we put a grid here and ask the question, what is his average velocity? What could we say? Well, he has run a total of 10 meters in 10 seconds, and it looks like his speed is very consistent, right? Each second, he covers another meter. So we would say it has an average velocity of 1 meter per second. If we wanted to add direction to that, we could say to the right, or to the east. What is his acceleration? Well, I think most of us have a conceptual understanding of acceleration as either speeding up or even slowing down. But in this case, we would have to say that his acceleration is 0, right? He is traveling at a constant average velocity. Now, let's run this again. Again, we'll take a snapshot every second of his position or displacement. So now let's put this grid up and compute what is the average velocity for each second or 1 second interval. So remember, we calculate velocity as the change in displacement divided by the change in time. So in the first second, he traveled 1 meter. So his average velocity would be 1 meter per second. Let's work a little further here. In the second, between 1 and 2 seconds, he traveled 2 meters. So now his speed is going to be 2 meters per second. Let's keep this up. In the third time interval, between 2 and 3 seconds, he travels a total of 3 meters. So we could say his speed or velocity is 3 meters per second. And let's do the last one here. The last 1 second interval, he travels from 6 to 10, so 4 meters in 1 second. So his average velocity or speed is 4 meters per second. So clearly here, he's not traveling at a constant velocity or speed. He is going faster and faster as he runs from left to right. Now, how do we describe quantitatively that speeding up? What is he actually doing? Okay. And we can answer that question by answering how much does his velocity increase or change each second? Well, we would say each second he is speeding up by 1 meter per second, right? He's going from 1 meter per second to 2 meters per second to 3 meters per second to 4 meters per second. But each second he speeds up by 1 meter per second, okay? So the way we would describe his acceleration with the correct units is what I've written down below here. I get my little pen. We know that he is speeding up 1 meter per second each second or per second, okay? Now, we can simplify this a little bit. The meter per second is in the denominator, and so let's put the 2 seconds together here, and we get these kind of unusual units for acceleration. And the way we would say this is 1 meter per second or 1 meter per second squared. Okay, but this is how we describe and quantify an object's acceleration. All right, let's officially define this now. So acceleration first is a vector quantity just like velocity and displacement, and it's defined as the rate at which an object changes its velocity. So let's start to describe this mathematically. Acceleration is equal to the change in velocity divided by the change in time, right? And if we use our math notation, here's how we would write that. We're going to use little a for acceleration. The line over it again means average. And then the triangle, remember, is delta, or change in velocity. So delta v over delta t is the change in velocity over the change in time. We can take it one step further, saying, well, what is the change in velocity? Well, we can take the difference between the final velocity and the initial velocity. Same thing we did with displacement when we were defining a way to calculate velocity, average velocity, and then divide that by the final time minus the initial time. Okay. So again, the symbol is little a, and the default units for acceleration will be in meters per second squared, just like we saw in the example of the running man on the previous slide. Now, notice since we've defined acceleration as the change in velocity, or the rate at which the velocity is changing, remember back to the previous lesson, velocity has two components to it. It has the speed, but it also has the direction. So a change in velocity can result from a change in the speed or a change in the direction. In other words, if the speed is changing, that is a form of acceleration. But also, even if the speed is constant and we're changing direction, that also is a form of acceleration. And the most common example of that is an object that is moving in a circle at a constant speed, okay? If you had a rock at the end of a string and you're spinning it around at a constant speed, it's still accelerating because the direction of that rock is constantly changing in order to maintain that circle. So that is what we call centripetal acceleration. We'll get into that more when we study circular motion. But for now, just know that if an object is changing its direction, that is another form of acceleration. Now, for the rest of this lesson, most of the examples we're going to look at is where the speed of the object is changing. That's the component of velocity that's changing, and therefore, how would we calculate the acceleration? All right, let's look at an example and see if we can apply this mathematical definition. So which car has the greatest acceleration? We have one car that goes from 0 to 60 meters per second in 5 seconds. And we have another car that goes to 0 to 80 meters per second in 10 seconds. Okay, so the question was, which one has greater acceleration? Well, we're going to use our formula. Average acceleration equals change in velocity over change in time. So let's go ahead and put the numbers in that. Okay, so our first, let's clear this. So here's the first case, right? We're going to put 60 as our final velocity, 0 as our initial velocity, and then we'll assume that our initial time is always 0 in these problems, unless otherwise stated. So the final minus the initial would be 5 seconds. So it's really simply 60 divided by 12, and we get this answer of 12 meters per second squared. Let's do the same thing for the second case. 80 meters per second divided by 10 seconds gives us a acceleration of 8 meters per second squared. Now, notice the car that had the greatest acceleration was not necessarily traveling the fastest at the end of the time period, okay? Just because something is traveling fast or faster doesn't mean it has a higher or greater acceleration. It all has to do with how much does the speed or velocity change per unit of time, okay, per second. And here we see that the first car was accelerating actually quite a bit faster, 12 meters per second versus 8 meters per second. That's about 50% faster. Now, If that first car had continued on for 10 seconds, right, it would have achieved a greater speed than the second car at 80 meters per second. So that's kind of my note here. Acceleration has nothing to do with going fast. A person can be moving very fast and still not be accelerating. They could be moving very fast at a constant velocity. All right, can acceleration be negative? Well, yes, if the velocity is decreasing, we say that that has a negative acceleration, and the math should agree with that. Okay. But here's the key thing. If negative, what direction is the acceleration relative to the velocity? So remember, both velocity and acceleration are vector quantities. So we do have to pay attention and specify the direction. So here's the key. If we are decelerating or slowing down, then the acceleration vector will be in the opposite direction of the velocity vector. Okay, now this really kind of is intuitive if you think about it, right? Because we may be moving left to right, but slowing down. So the acceleration has to be acting in the opposite direction in order to cause it to slow down. Okay, so that's the rule of thumb. If we are slowing down, the acceleration will be in the opposite direction of whatever the velocity direction is. So let's look at a quick example here. We've got a ball moving down a ramp, okay? So let's see, I think its velocity would be down the ramp. And since it's speeding up as it goes down that ramp, its acceleration would be in the same direction. Okay? Speeding up, same direction. Now, what happens if that ball rolls up the ramp? Well, we know if we give it a roll and it starts to go up the ramp, it's going to slow down as it goes uphill or up the ramp. So even though its velocity is still up the ramp, because it's slowing down, its acceleration direction would be opposite, down the ramp. Okay, so that's the rule of thumb for how we can remember what direction the acceleration will be. Speeding up, same direction. Slowing down, opposite direction of velocity. All right, let's look at one more example here. We're gonna let this object go down this ramp, okay? And then it's going to hit this level stretch of the track and then go around the curve and then hit another stretch down below. So clearly, when it's going down the ramp, assuming very low friction, it will be accelerating as it goes down. Then once it hits the flat spot, it's going to slow down. It will continue to slow down as it goes around this track, okay? So let's put this little animation into play here. Let's see if I can get it. There we go. Now notice the blue vector is for velocity. The green vector is for acceleration. Okay, so let's see if these rules of thumb apply by watching the animation. Now, when it's going down, they're both in the same direction. But notice on the rest of the ramp, while it's slowing down, the acceleration vector is in the opposite direction of the velocity. We'll watch it one more time here. Now, you may have noticed when it goes around that turn, the velocity or the acceleration vector points into the center of that turn. This is an example of what I talked about earlier of the centripetal acceleration when an object is changing its direction, and going in a circular path is the most common example of that. So again, we'll get into that more when we get into circular motion. All right, let's look at another example here. Find the acceleration where an object, this car, is going from 60 meters per second to 0 in 4 seconds. Okay, so we're slowing down. Now, I mentioned the math should always agree. So if we consider his velocity to be positive, and we plug it into our formula, we should get a negative result because we know the acceleration needs to be in the opposite direction. And the positive and negative sign would tell us that they are in opposite direction. So let's plug it in, right? Notice in this case, our final speed is 0 meters per second. So that's what we're going to start with, right? So 0 meters per second minus 60. 60 is our initial, but we're always taking the difference. So make sure we have the subtraction in there. And then the time of our final is 4, and we started at 0. So that's just going to be 4 seconds. So if we do the math, right, we basically have negative 60 divided by 4, and it gives us a negative 15 meters per second squared. Okay, so the negative, if we wind up with a negative value, we're plugging into our formulas for acceleration, it tells us that we're decelerating and that the direction will be opposite that of the velocity if we assume or call the velocity the positive direction. Okay, so that's our lesson for today. There is a short Google worksheet that goes with this. Please go ahead and complete that. You'll find the rest of the instructions in Google Classroom.